All right, hello, and welcome to today's webinar, Legionella Control in Healthcare, a comparative discussion of chlorine dioxide and monochloramine. My name is Alex Whitmore, and I have the pleasure of introducing two distinguished experts who will be sharing their knowledge and perspectives on this topic. We also have a few poll questions you have the ability to answer. You'll notice in Zoom a few of those have popped up. Please take a quick moment to fill these out as I begin our introductions. Firstly, I'm thrilled to introduce Dr. Alberto Camazzi, a Vice President of Business Development at Sanapure US. He's based out of Philadelphia. Dr. Camazzi holds a PhD in Industrial Chemistry, is a certified Legionella Management Specialist, and a member of numerous recognized water treatment committees. Dr. Camazzi brings a wealth of knowledge and experience to today's discussion. Joining him is Mr. Andrew Brink-Dopke, the Vice President of Engineering and Technology at PureLine. As a chemical engineer, Andrew has over a decade of experience in chlorine dioxide design and application, and an extensive background in water treatment and piping systems. His expertise in application design, system design, automation, and optimization will undoubtedly enrich our conversation today. Before we begin, I would like to remind the audience to please feel free to submit questions throughout the event using the Q&A feature on your webinar toolbar. Our speakers will have some time at the very end of the presentation to address questions. Any technical questions you may have will be addressed as soon as possible. Please also note that information on how to view the recording of today's webinar will be sent in a follow-up email. At this time, I'd like to turn our attention to Alberto, who will dive into monochloramine with us today. Take it away, Alberto.
Thank you, Alex. All right, let's get started with this webinar. Thanks for the introduction. This is the agenda for today's presentation. We're going to start with a little bit of introduction about Legionella and how Legionella gets in the buildings. And then I'm going to cover the monochloramine part. So a little bit of monochloramine benefits, the chemistry of monochloramine, and the available technologies. And then I'm going to turn it over to Andrew, where he will cover the chlorine dioxide part, and then we'll open for question and answers at the end. So Alex already did the introduction, so I don't have to go over who I am again. So let's just get started with the Legionella part. I think that at this point, there has been enough discussion in the United States about Legionella. So I'm pretty sure that everybody knows what Legionella is, harmful waterborne pathogen. If a person breathes in the water droplets with the Legionella germs in it, can get sick, can develop a severe pneumonia, especially if that person is immunocompromised. But I think that for today's call, it's more beneficial to understand how Legionella gets in the building plumbing systems and what can we do to mitigate the risk of somebody getting sick in buildings. So the public water supplies usually carry out two different disinfection steps when they get the water from the reservoir. The first one, it's called primary disinfection, is usually carried out with either chlorine, so bleach, or chlorine dioxide. And that step is meant to inactivate viruses and bacteria in the water. The second step, it's called secondary disinfection, which is usually done with either chlorine or monochloramine. And that it's done in order to provide a residual throughout the municipal distribution system. Also, the disinfectants that are being applied in building, which is what we are going to talk about today, are either called secondary or supplemental. Just want to throw it out there so everybody gets familiar with the terminology. Now, the public water utility disinfects the water, and technically, that disinfectant is supposed to kill, as we said, the viruses and bacteria, but Legionella is so strong that can survive both disinfection steps. So those little germs that survive the disinfection steps will at some point enter a building water system, and even if the levels at the point of entry are usually below the detectable level, Legionella becomes a threat when it enters building just because of the environment of a typical plumbing system. So we have very small pipes that offer a much higher surface to volume ratio, so where the biofilm can grow. In a building, we have warm water temperature, such as domestic hot water system, as in cooling towers. And also, if we think about hospitals, there's a much higher occupants exposure, right? Like with more immunocompromised people. So Legionella in the US, if we look just at numbers, we can see that the CDC published this graph that says that in the last 20 years, the number of Legionella cases increased by a 10 times factor approximately. And there is not an enforceable limit for Legionella levels when the public water utility delivers the water to the distribution system. So in other words, the municipality treatment plants doesn't have to test for Legionella, nor the buildings have to test for Legionella. But if something happens in a building, the building owner and the building managers are going to be the one responsible for that Legionella case or outbreak, because at the end of the day, they are the ones that are responsible for the safety of the occupants of that building, whether that building is a hospital, nursing home, or other commercial facilities as well, such as hotels, casinos, and resorts. A big step in the US Legionella market was made in 2017 when the CMS, the Center for Medicare and Medicaid Services, published a memo saying that all healthcare facilities needed to implement a water management plan, which was in line with ASHRAE Standard 188, in order to mitigate the risk of somebody being sick and getting sick from Legionella in their building. And if healthcare facilities didn't do so or don't do so, they're not going to be eligible to receive any more federal fundings. So, at the end of the day, healthcare facilities needs to implement or, required to implement water management plans. And the Joint Commission started to actually audit healthcare facilities from the beginning of 2022. Because, a facility can have a plan, but then the plan needs to be implemented in order to work. So because of these requirements, definitely the demand for supplemental disinfection technologies in buildings increased in the last 5 to 6 years. Typical supplemental disinfection technologies are chlorine-based disinfectants that are EPA listed disinfectants under the Safe Drinking Water Act, which are typical chlorine and chlorine dioxide and monochloramine. As well as buildings are implementing other technologies and strategies to try to mitigate Legionella in their plumbing system, such as copper silver, ozone, Myox, and also short course remediation, such as heat and flush or hyperchlorination. So speaking about monochloramine and the benefits of the molecule, it's definitely a much milder oxidant compared to chlorine and chlorine dioxide. And because it's more stable, it does not decay as fast as other disinfectants. So it lasts longer, either on a public water utility distribution system or in a building plumbing system. Because it's more stable, will be stable at warm water temperatures. So other disinfectants may decay pretty fast in domestic hot water systems, whereas monochloramine does not. And because of that, it's going to be in a building plumbing system much easier to establish a consistent residual of monochloramine everywhere in the plumbing system, even in those areas where there is low flow or there is not a lot of water use. And again, because it's a milder oxidant, the oxidation power of that molecule is not going to be as high. So it's usually less corrosive towards plumbing components compared to other choices. Monochloramine is not an acid dissolved in water, so it's not pH dependent. And because of that, it doesn't matter of the pH level of the water in the building. The monochloramine effect on pathogens is not going to be influenced by the pH of the water. Monochloramine does not react with the organics that are normally found in water. And because of that, it doesn't produce disinfection byproducts, which are thiazomethanes and haloacetic acids, which are carcinogenic products. And because it doesn't react with organics, monochloramine can fully penetrate the biofilm. So that polymeric matrix that is attached to the pipe walls, which ultimately it's where the organisms will grow and start to colonize the plumbing system. I just want to show you case study from a paper that was published in 2021 by the US EPA about monochloramine. This was a paper that was published with the results gathered from a medium-sized healthcare facility in Ohio. This hospital started to have Legionella problems in 2013, even though they had pretty good residuals, chlorine residuals coming in from the municipality. You always have to keep in mind that even if you have a good level of chlorine coming in from the city, that doesn't mean you're going to have a good chlorine level in your plumbing system. In 2014, they ran another round of samples and realized they had a 71% Legionella positivity on their domestic hot water system. The hospital decided to perform some short course remediation, such as heat and flush. But even though the Legionella levels decreased right after the treatment, they started to climb back up shortly after. So that's why the facility decided to install a monochloramine system on their domestic hot water system. The Ohio EPA was involved, and they were already gathering water chemistry data and microbiological data before the monochloramine system was applied in the building. And then they kept gathering that data after the system was installed, because the goal of the studies were to evaluate the effect of monochloramine, not just on Legionella, but on other pathogens like Pseudomonas or non-tuberculosis mycobacteria, as well as evaluate the impact on the water chemistry when monochloramine was being added to the hot water system. In particular, they wanted to monitor nitrification, if there was any increase on disinfection byproduct, pH, lead and copper, and other metals in the water. The results of the study reported that with monochloramine levels between 2 and 2.5, which that is the sweet spot for monochloramine, and low free ammonia level, they had good they actually had great microbiological results. They were able to notice a great decrease on the Legionella positivity, Pseudomonas, as well as non-tuberculosis mycobacterium, as well as they didn't notice any impact on the water quality whatsoever. So there was no effect on nitrification. There was no increase in disinfection byproducts, as well as no increase in the corrosion rates of the plumbing system. Now let's see, let's talk about the monochloramine chemistry. So how is monochloramine being fed into a building water system? So usually monochloramine is produced on site as needed. So there is not a tank with a 10% solution of monochloramine. There are monochloramine generators that generate monochloramine based on the demand of the building. And usually the precursors are sodium hypo, so bleach, and either ammonium chloride or sulfate. And I always make the point that ammonium chloride or sulfate are two salts. They're not liquid ammonia. And also, because monochloramine is being formed between a chlorine source and a nitrogen source, it's very important the ratio between the two. The monochloramine system that Sanipur supplies, it's a complete package system. So everything comes pre-wired, comes pre-mounted from factory. The piping gets made in high purity PVDF, and all our generators have all the needed safety features, which I'm going to show you in a couple of slides, because 99% of the applications that we make are made on potable water. All our generators are 24/7 remote monitored, and people have access to that. The operators have access to check the units online, and all our assembly is certified to NSF standard 61, and the precursors that we use are certified to NSF standard 60. We do have 3 types of generators, 3 different sizes. The chemistry is the same. It's just different sizes of the dosing systems. The first one is called the Sanikill Light, which is the generator that is commonly used in nursing homes or small hospitals, and that can treat peak flow rate of about 40 gallons a minute, 40 to 50 gallons a minute. The second size up is called Sanikill 1. That's a unit that it's usually being implemented in medium to big hospitals, commercial buildings, hotels, big apartment complexes. So where the water demand, especially in the morning or in the evening, can be pretty high. So these units can treat peak flow rates up to 250 and 300 gallons a minute. The last size is called Sanikill Tech, which can treat peak flow rates higher than 2,000 gallons a minute. And that's usually a unit that is being installed for an entire campus, or for processed water as well, such as cooling towers. Typical installation of monochloramine generators. Monochloramine, it's usually fed to the plumbing system based on water flow. So there is a flow meter that comes with the unit, measures the water flow, and the system automatically adjusts the feed rate to maintain a certain residual in the building water system, as well as ORP or total chlorine can be used to trim the feed rate of monochloramine in the building water. The system can be installed either on the incoming cold water, so to treat the entire cold water of the building, or can just be installed directly on the domestic hot water system, which for monochloramine, it's usually preferred for 3 or 4 different reasons. The first one is that Legionella does not colonize on cold water. As we said, it comes in from the city in your cold water main, but usually starts to spread around in the building once that bacteria reaches the domestic hot water system. Plus, the cold water consumption in buildings, it's usually 90% higher than the hot water consumption. So that means that bigger units and much higher volume of chemicals are needed to treat the entire cold water system. And plus, there is also lower exposure for building occupants when just the hot water is being treated because people don't usually drink the hot water that comes from the tap. Typical precursor sizes for hot water installation are between 5 to 15 gallons a month of each precursors based on the water consumption of the building, rarely 30 gallons drums. For cold water application, we're definitely talking about like bulk tanks or totes, so 200 gallons per month or more. Typical installation on a domestic hot water system, the system is installed, the monochloramine system is installed on a side stream on your domestic hot water supply. So if there is any mix involved, we only require 2 taps, 2 3/4 taps. We supply a circulator with which we pull about a couple of gallons a minute through the generator. The generator measures the hot water consumption by measuring the cold water intake to the domestic hot water system and feeds based on that. So we're looking at levels usually between 1.5 and 3.5 parts per million of monochloramine in your domestic hot water system. Also, the beauty of feeding monochloramine on the domestic hot water system is that the water is always circulating. So it comes back from the domestic hot water return. So we can actually monitor what's coming back from the building and adjust the feed rate based on that as well, even during times of the days when there's not much water consumption, such as 2 o'clock in the morning. Safety features of the generators. Level sensor that can be installed in the tank, typical open-close level sensor or analog level sensors that can tell the level in the tank at any point in time. Flow sensors on each reagent line, that's the picture in the middle. So every time that the pumps feed the chemicals, each one, the flow sensor are going to measure how much chemical is being injected and to make sure we maintain the correct chlorine to nitrogen ratio. Or if any of the dosing pump has any issue, there's no point in feeding just one or the other chemicals. As well as there are flow sensor on the piping assembly of the unit to measure the water flow through the reactor, the temperature, the ORP, and the total chlorine. Remote connectivity of our systems. Each system is connected to our server. Once the system is connected, we build this page, which is fully customizable. People can plot any data that they want. There is data recording with no storage limitation, and people can access this page at any point in time, as well as they can download the report from the page. Operators that are allowed to service the unit can change the settings of the unit. As well as if there is any problem with the unit, such as the level in the tank is low, the operator will receive an email and a text message right away saying that that was the problem. So to summarize monochloramine, the monochloramine, it's again one of the EPA listed disinfectants that showed great efficacy against Legionella and other waterborne pathogens. It is a milder oxidant compared to other chlorine-based disinfectant. And because of that, it's much easier to establish a consistent residual everywhere in the plumbing system. For monochloramine application, hot water installations are preferred if Legionella is the target. And also let's keep in mind that regardless of the disinfectant that is being applied in the system, flushing is always the key point of a successful supplemental disinfection application in a building water system. So with that, I'm going to turn it over to Andrew. I'm going to stop sharing my screen. And thank you very much.
Thanks, Albert. Appreciate it. Hi, everybody. I'll go over again just because it was presented at the beginning, but my name's Andrew Brinktowke. I'm the Vice President of Engineering Technologies at PureLine. I've been responsible for designing chlorine dioxide equipment and water treatment applications throughout the medical, food, and beverage industries for the last 12 years. I spent over 15 years doing various water treatment from municipalities all the way through to wastewater treatment applications. So, and Alberto pointed this out, there's a lot of terminology, used to be called secondary water treatment for treatments at facilities. Now that there's primary and secondary water treatment at municipalities, it gets a little muddled, but when I refer to secondary water treatment, it's water treatment after it's been received as treated water from the municipality. So for secondary water treatment in facilities, there's no one size fits all. I mean, we all want a solution that will work with no work required, no thinking about it, and it's just a magic pill that fixes everything. But that's usually not the case. Chlorine dioxide is one of the few options that shows really good effectiveness and long-lasting reduction and elimination of biofilms and Legionella in piping systems. But it's not just I installed it, everything's great. Some buildings, just reviewing your systems, your water management plan, how you flush your systems can be enough to eliminate your risks. But in a lot of old piping systems, and depending on the water supply in that area, it's often not enough. So, secondary water treatment is not required, but in a lot of applications, it's the only way to keep these pathogens out of the water system. So any facility that's considering putting in a treatment plan should always consult with their local and state for regulatory and permitting requirements. Any secondary water system, anything you're going to inject into the water at these public facilities is going to need to meet whatever their standards and regulations are. When you're considering it, again, no matter what your treatment plan is, dead leg sanitary design of the piping system, avoiding those stagnations, getting flow to every wing, every deadhead, every spigot and faucet periodically is absolutely crucial to maintaining good control. There's just nothing that can supplant getting fresh water with sanitizing solution in it to every point on a frequent basis. So what is chlorine dioxide? Chlorine dioxide, has chlorine in it, but it's not chlorine. It's just a relative of it. It's a chlorine with 2 oxygen molecules attached to it. So it exists as a gas that is readily absorbed into water, so much like oxygen or ozone. It is a yellowish greenish color, and it's used throughout municipal water treatment, wastewater treatment, food and beverage, hospitals, all these industries, cooling towers and chill loops, as a really effective, fast-acting biocide for biofilms, pathogens, all sorts of waterborne things. It's not new, but chlorine dioxide was discovered over 200 years ago by Sir Humphrey Davy. It started to be used in the United States in the early 1900s, for odor control and general water quality in the States. By the 70s, there was thousands of municipalities using chlorine dioxide for treating water. Its huge uptick came in the pulp and paper industry. That's where a huge percentage of the chlorine dioxide that's produced is used, because it's a really effective bleaching agent that's not as harsh on pulp and paper material statistics, or how that makes a nice soft paper, whatever. It's the similar properties that make it a good water treatment chemical, in that it's really selective in how that it works and doesn't provide a lot of the harmful degenerative aspects of like a chlorine or a bromine treatment. By the 90s, secondary treatment, as I call it, after, in hospitals, nursing homes, hotels, facilities, started to really become a big thing, especially in those areas where the water quality coming to them wasn't as good, or the plumbing systems were a lot older, a lot of iron scale and stuff that really promotes the growth of bacteria. And then came, with now in the 2000s, new materials, controls, electronics upgrades, cost reductions in these materials has really led to smaller, more compact, more reliable, safer systems for distributing and generating chlorine dioxide, so that it's readily available and feasible for even the smallest applications. So we've talked about it a little bit, but what does it mean that it's not chlorine? It's not bromine. Why is it different? How is it different? So it's chlorine dioxide, unlike like chlorine is a gas, but when chlorine dissolves in water, it dissociates into hypochlorite and hypochlorous acid. And the hypochlorous acid is really the effective biocide there, but that's pH dependent. The higher your pH goes, the less hypochlorous acid you have. Chlorine dioxide is chlorine dioxide, both in the gas and liquid phase, so the pH doesn't affect it. And unlike being an ion, which can be rejected by the cell walls of biofilms and bacteria, chlorine dioxide it's a dissolved gas like oxygen or ozone. It passes through the cell walls, so even dead and dying bacteria, biofilms on the surface of pipes, the chlorine dioxide gas can continue to pass through those, where the chlorines and bromines are usually stopped by a layer of dead biofilm layer, and the underneath is protected. And then once the chlorine or bromine isn't there, it continues to regrow. It's not as strong of an oxidizer as ozone or peroxide. It's only got a 0.95 electron volt. That's just how strongly it can pull electrons off of things. Oxidation strength, but it has a lot of oxidation capacity. So chlorine dioxide can remove up to 5 electrons from cell walls and bacterial cell structures in its oxidation, which allows it to be dosed at lower levels than chlorine and have superior effectiveness. So whereas chlorine may need a 1 or 2 part per million level, chlorine dioxide can be just as effective or better at a 0.2, 0.3, 0.4 ppm level. Where is it used? I've kind of touched on it here and there, but it's, chlorine dioxide is used initially in municipal water treatment, so to knock down organics and bacteria and pathogens before the use of chlorine or bromine, so that THMs and other disinfection byproducts aren't created. Chlorine dioxide, because it works as a free radical and not as a chlorinating compound, doesn't produce the disinfection byproducts. It's used so past that primary treatment, then it's again used in secondary water treatments in nursing homes, food plants, anywhere where, again, those really persistent pathogens and things that can enter the water system through leaks and disturbances find their way into facilities. It's used in secondary water treatment to then make sure those cannot thrive and grow in those systems. Well water treatment for iron and mineral control, as well as biofilms and E. coli. Processed water for condensate, RO permeates in the food and beverage industries. And then wastewater cooling towers, chilled loops, wash water systems, CIP systems, all kinds of those applications in water. So Legionella is often found in biofilm. We've discussed this, and it offers it a level of protection, and that's why we have to talk about these specialty chemicals in order to eradicate it. It's why the chlorinated water systems that supply water still don't eliminate the problem. And again, it's why chlorine dioxide is one of those few go-tos that will work, is that much like ozone, its penetration through the biofilm layer is almost unparalleled and will attack it all the way to the surface of the pipe, killing everything, including the interstitial bacteria, which are holding that biofilm to the pipe, which eventually then allows it to flush everything out of the system, leaving little to nothing behind. And biofilms often can be seen, very often felt, and it's a thin, slimy residue on the insides of pipes and fittings in the water systems that you have. A couple case studies that just kind of identify the levels and the effectiveness of chlorine dioxide, especially in hospital systems. Are a couple listed here where 0.25 to 0.5 milligrams per liter, which is parts per million, injected into cold water supplies and hot water taps, hot water loops, and both these cases, Legionella was prevalent. It was an issue. In the first case, after 3 years of treatment, Legionella wasn't detectable in the water system anymore. In the second one, which is a Johns Hopkins study, initial reductions were good but not fantastic. But over the period of 17 months, levels were dropped by over 90%, and then remained low throughout the remaining time. General application design. So again, the typical target is about a 0.5 ppm residual. Depending on the systems, the application, the condition of the piping system, lower residuals may be just as effective, but a 0.5 is a good place to start. Hot water loops can typically be lower. The warmer water makes the molecules more active. Chlorine dioxide is more effective at lower dosages, so a 0.2 ppm is usually a target residual in a hot water loop. Any demand in that water obviously has to be met first, so iron, manganese, other organics that could possibly eat up chlorine dioxide have to be taken into consideration. But in terms of secondary water treatment, those demands are usually very low. Unless the water system is incredibly foul, those will be a low number. So when we talk sizing, we don't take a huge load in the water to be considered. And then for sizing, it's the flow rate and total usage volume of the system is considered. The basic sizing calculations. So typical chlorine dioxide treatment will treat the cold water and the hot water for a facility. Calculate your need in terms of pounds per day of chlorine dioxide, which is the typical way that systems are sized for chlorine dioxide. Daily water usage, which can usually get, usually you can get a monthly or a yearly water usage number and then determine a daily average. Multiply it by the density of water, divided by 1,000,000, and that'll give you the amount of chlorine dioxide for a 1 ppm dose. And when we size a system, we'll size for a 1 ppm dose because that will conservatively be more than enough to deliver a 0.5 ppm residual. You may not run it at the rate that's listed here, but if your system is sized for it, you have that available capacity in the system. It's also important to consider peak. So the average just tells you this is how much chlorine dioxide you should use on a daily basis. But in order to be able to treat your water at the proper levels throughout the day, you have to know what those minimum and maximum flow rates might be that you need to treat. So you take a maximum flow rate multiplied by the density, and time conversions to get your pounds per day rate that any pump or distribution system would need to meet. Typical hospitals, we treat them all over the country, about 75 to 150 gallons per day per bed. Because most of the time there's not 100% occupancy, that number generally leads to a fairly accurate calculation of water usage for that facility. So a 250 bed hospital is about a 25,000 gallon per day water usage, and we can use that for calculating what size of system or how much chemical might be needed. Dosing control, chlorine dioxide. When we dose it to the domestic cold water coming into the building, there's a flow meter on that typically. If not, one can be installed, either a non-contact or an insertion-based flow meter, and that flow reading is ported directly to the chlorine dioxide system, be it a generator or a dosing system, to control dosing pumps to deliver chlorine dioxide proportional to the flow. A secondary trim control can be added. Chlorine dioxide has inline monitors for continuously monitoring the chlorine dioxide level. So you can apply those to trim the speed of the pump. So if you're a little high, it turns the pump down, a little low, it turns the pump up to maintain tighter control of your desired residuals. Hot water loops have constant flow, but intermittent water usage, so you can't base your treatment on flow. Here, we base it on a residual or an ORP in the system and dose chlorine dioxide with an on-off control to maintain adequate levels in the loop. A example of a typical hot water loop design, the dispensing system injects into the outgoing water from the heat system, and chlorine dioxide levels are measured on the return. And again, a dead band control is typically what's employed here. Chlorine dioxide levels fall below X amount, system comes on and adds chlorine dioxide. When they reach Y amount, the pump stops and repeats that cycle over and over. In order to measure the chlorine dioxide, the commercially available technologies for it, sample coolers are used just to bring the hot water back down to room temperature. Most of the analyzers use a very, very small amount of water to take the measurement, and that's typically around 1/8 of a gallon a minute, which just usually runs the drain. An overall schematic of a hospital water treatment system is a chlorine dioxide system, which could be a dispensing system for pre-made chlorine dioxide or a generation system. You can see the domestic water flow meter signal is brought back to the unit. Residual analyzers on both the cold water and the hot water. The cold water is an optional one, but provides backup and tighter control if desired. So the system doses the cold water based on flow and the hot water based on the residual. There's a sodium chloride or a chlorine dioxide supply to make the chlorine dioxide for use, and a city water supply for collection or operation of the equipment. So I talked about could be pre-made chlorine dioxide or a generator. Chlorine dioxide is available in 3,000 ppm solution. With that, if you're using 3,000 ppm, a 55-gallon drum can treat about 330,000 gallons of water at a 0.5 ppm dose. So if there's very little load in the system and water, and a 0.5 ppm dose gives you the 0.25 to 0.5 ppm residual, then you can size it based on this. So a facility using 30,000 gallons a day could operate for around 11 days on a single drum of chlorine dioxide. Smaller hospitals and systems using even less water can obviously operate for weeks or months at a time on a drum of chemical. If you're using a pre-made solution, pH neutral byproduct free chlorine dioxide this is really the only option that you have. Anything else made by acid generation isn't really stable. It's not as good from a corrosion standpoint on the systems, and will give you higher levels of production byproducts. So electrochemical fluorine gas-based chlorine dioxide generation, which will produce a pH neutral chlorine dioxide solution with no byproducts in it, is the way to go. And if you pair that chemical with an accurate automated dosing pump and a good facility water flow meter, you have a secondary water treatment that will provide continuous coverage of your premises' water day in and day out with very little maintenance or upkeep requirements. For the larger systems where pre-made is no longer an option, so where you need, a half a pound or more a day of chlorine dioxide, chlorine dioxide generators are available, again, for corrosion and disinfection byproduct mitigation. Electrochemical generation is recommended here. With those systems, sodium chlorite is used in electricity to make chlorine dioxide, so there's no concentrated acids on site. The chlorine dioxide gas, the property of chlorine dioxide is taken advantage of here, where the chlorine dioxide gas molecule is generated, transferred to a clean water stream, and that becomes the chlorine dioxide source for treatment. So none of the unreacted chemicals, no unwanted byproducts from any reaction, just pure chlorine dioxide in the water is used to treat the system. And they're also readily controllable with online analyzers for concentration and 24/7 remote monitoring to ensure that you're getting the right levels of chlorine dioxide all the time. And these systems are designed to produce 0 to 40 pounds per day of chlorine dioxide versus a 55-gallon drum may have 1.5 pounds of chlorine dioxide in it. These generators can produce that every day, if not many of those every day. So they're usually designed for systems using 10,000 to 10 million gallons a day of water. One example, pre-made is Pure 3000, which we produce, and it's a 99.5% pure chlorine dioxide solution, that being chlorine dioxide versus any other chlorine species in water. It is primarily water. It is NSF 60 certified, EPA and FDA certified, and EPA label as well. And it's ready to use non-hazardous solution for chlorine dioxide applications in small to medium-sized facilities. From a generation perspective, this is an example of an electrochemical generator. This is the HP series from PureLine, which is a WQA, or sorry, the NSF ANSI 61 certified for the generator, and the product it produces, which is Pure 3000, is NSF 60, all third-party certified. These systems utilize a sodium chloride solution called Puricide E, which has ANSI NSF 60 certification as well. They come with highly sophisticated, state-of-the-art 1,000-to-1 turn down dosing pumps with DC brushless motors, really, really sophisticated systems. The last 10 years has really seen a huge improvements in capabilities and reliability and cost effectiveness of these types of metering pumps, which really goes to controlling and maintaining your treatment systems. Flow pacing, residuals, remote on-offs, remote monitoring, alarms, text and email messaging is all available on systems like these. So in summary, again, the biggest thing is, there's no one size fits all. Chlorine dioxide is a great chemical. It can be applied in a tremendous number of situations to alleviate or prevent issues when it comes to biofilm and Legionella, but it's not the only solution, and it's probably not just adding it. Water management procedures and processes will go hand in hand with having effective treatment. Chlorine dioxide is fast acting, so results are typically days to weeks after implementing. The ready to use solutions are really great for small hospitals, nursing homes, food plants, bottling beverages, sanitization purposes, versus having complicated generation systems with things that have to be monitored, constantly, a lot of moving parts. A simple pump and container system is great for those applications where you just don't have the manpower to maintain them. Chlorine dioxide is easily measured both manually and online for tracking, reporting, and confidence that your systems are working properly and that your water has the right levels of treatment in it. And again, I thank you all for your time.
That's great. I'd like to give a big thank you to both Alberto and Andrew for today's presentation. At this point, we'd like to turn to our Q&A portion of the webinar. If you have any questions from today's discussion, please submit these through the webinar toolbar. I think you can find it either at the bottom or the top of your Zoom application. Additionally, if you have specific questions for either Alberto or Andrew, you are welcome to write down their contact information as seen here and send them an email with your specific inquiry. We did have a question that came up saying, will a recording be made available? Yes, absolutely. A recording from today's webinar will be made available soon. You can keep an eye out for a follow-up email with information on how to view the recording. With that, it looks like we have a question coming in. Are there any special exhaust requirements at the generator? So I'm not sure if this is necessarily a chlorine dioxide or a monochloramine related question, but I'll kind of open up to Andrew to get started. And if you want to address it as well, Alberto, you're welcome to. The question is, are there any special exhaust requirements for a generator?
So if you're utilizing pre-made chlorine dioxide, depending on the level of system, so we have, there's systems where they have a built-in onboard tank, and chlorine dioxide is transferred from shipping containers into it. Typically, that is either the onboard tank has to be vented to the outside, or a carbon filter is used, which is a replaceable item you typically replace every 2 to 3 months. The generators, the new age of generators, depending on which one you get, the HP series version of it doesn't have any required ventilation anymore. It has built-in regenerative seal pot systems for doing it. There is a small bit of hydrogen produced, so if the room is not adequately ventilated, which most are, then you would have to run an outside vent to discharge that line. But other than that, no significant venting required. We have applications now 2-3 stories underground with no ventilation.
Great, thanks, Andrew. Alberto, do you want to answer that for the monochloramine generator?
Yeah, sure. Well, for monochloramine generators, there are no exhaust requirements and ventilation requirements, just because the monochloramine is generated within the water stream. So there is never a point in time there is a highly concentrated monochloramine solution that is being stored where the generator is. It's basically being generated at drinking water levels. The only requirements that are in place are for the precursors, not for the ammonium chloride part, just because that's a salt dissolved in water. It's just for the hypo, and those are just requirements that are typical for, when bleach is stored into a facility. So basically just have a ventilated room. That said, usually these systems are installed in mechanical rooms in buildings, whether they are healthcare facilities or commercial buildings. So usually mechanical rooms are already ventilated, so there are not there's usually never a requirement to like build a fan that to bring the exhaust out on the outside.
Thanks, Alberto. Follow-up question was, can the systems be tied into a facility BMS system?
Or I'll take these first, and then I'll let Andrew answer. Yes, actually forgot to mention that during the presentation. The system can be tied to the BMS either through digital inputs or analog inputs. So 4 to 20 milliamp, either Modbus or BACnet. So either one. Thank you.
Yeah, and likewise for the equipment shown here, doesn't speak to all chlorine dioxide systems, but the one shown here run on Allen Bradley based systems. So you can take discrete inputs and outputs for run statuses, or connect over Ethernet IP through a Cat5 cable to monitor all the parameters in systems, as well as systems are available with cellular remote connection, which allows it for text and email communication of reports and alarms.
Great. Well, I think that is the completion of our Q&A section, unless there are any last burning questions that need to get submitted. Once again, a recording from today's webinar will be made available soon. Please look out for a follow-up email with information on how to view the recording. And thank you for attending today's webinar. We hope you have a great rest of your day, and thank you for your time.